All right, welcome everybody. This is our 7th week of talks in the GCOOS Spring Webinar Series. Our goal is to share the research that's being funded by GCOOS principal investigators under our new IU's 5-year award. My name is Chris Simonello. I'm the Outreach and Education Manager for GCOOS, and I'll be moderating today's session, which is being recorded. Jennifer Vreeland will also be helping to monitor questions that you can ask by either raising your hand or writing in the chat box. There'll be time for questions after each speaker. First up today is Dr. Beth Stauffer. Beth is an associate professor in the Department of Biology and the Slemko LEQSF Regents Endowed Professor in Science 2 at the University of Louisiana at Lafayette. Her research is focused on understanding how physical, chemical, and biological environments interact to shape phytoplankton communities in coastal waters, especially how the food webs they support vary across gradients of ocean acidification, estuarine change, and in response to extreme weather events. And building on the work she conducted as a AAAS Science and Technology Policy Fellow, she continues to develop capabilities for continuous nutrient sensing. She's working with multiple agencies, including the EPA, GCOOS, and the Alliance for Coastal Technologies, to test the deployment of an affordable wet chemistry nitrate sensor to assess integration into existing monitoring programs. And her talk today is entitled Envisioning, Building a Nutrient Sensor Network in the Gulf of Mexico. Following Beth's talk, I'll introduce Bob Leben. So all yours, Beth.
Great, thank you. Can everybody hear me okay? Yes. I've got, let me pull up my presentation really quick. Hopefully let's see, is ready to go. Okay, Chris, can you confirm that you're seeing the right view?
I see it, but I still see your next slide in queue on the right.
That's weird.
You're not full
Let's
screen
try.
yet. There you go. Perfect.
Let's try that. Okay, perfect. Thank you so much for asking me to speak today. We're really happy to be part of the GCOOS family and building on some work that I've been doing for many years now that's focused on nutrient sensors and trying to kind of build more capacity for nutrient sensing, specifically in the Gulf of Mexico. This is a collaborative project. We've got partners in Florida, in Louisiana. We're hoping to expand this partnership, so stay tuned for that in a few minutes. And as Chris said, we are funded through GCOOS, funds from kind of EPA and IUs who have been real supporters of this work since its beginning. This work was previously funded and kind of coordinated through the Alliance for Coastal Technologies, which has just kind of ended its run of more than 20 years of trying to support technology advancement for ocean and coastal sciences. And so lots of people to thank, lots of partners and funding to point to as well. I'm not going to belabor the point or preach too much to the choir, especially GCOOS, the Gulf of Mexico part of GCOOS, right? I think we're all super aware of the issues related to nutrient pollution, whether it's the downstream issues of eutrophication, hypoxia, or harmful algal blooms. I think we're all probably pretty aware as well of the programs and goals that have been established to try and monitor and ultimately reduce nutrient pollution. So things like total maximum daily loads in Chesapeake Bay, but of course we know that TMDLs are not restricted to Chesapeake Bay. This upper map shows the number of TMDLs kind of throughout the country, not to mention worldwide. And then, of course, we're in the Gulf of Mexico, right? We're all aware of the issues related to Gulf hypoxia and dead zones. And of course, we know that the Mississippi River Gulf of Mexico Watershed Nutrient, aka Hypoxia Task Force, has set this goal, has recently revised this goal to really try and reduce the aerial extent of that hypoxic zone through nutrient reductions going forward. We also know that the success towards some of these goals is challenging. This is from the most recent report to Congress from the Hypoxia Task Force, showing that we're not quite where we need to be in terms of reducing these zones of reduced reducing the zones of decreased dissolved oxygen. We know that, and I think Jen was mentioning this just a minute ago, right? We've got an ongoing red tide Karenia brevis bloom off the coast of Florida right now. We know that both of these are strongly tied to nutrients coming into the system, right? Whether it's through the Mississippi River watershed impacting that hypoxic zone, or it's nutrients coming into and persisting in the coastal zone, supporting these Karenia brevis blooms kind of once they've been transported or kind of reached the coast. And so we've done some work in the past and folks at USGS and in the research community have done some work in the past that has shown that the way we are currently trying to understand some of the, for example, nitrogen loading that's impacting the Gulf of Mexico dead zone, some of the ways that we can estimate how much nitrogen or phosphorus or other nutrients are available in coastal Florida to support those red tides. All of those estimates can be enhanced, can be improved by basically having better, more temporally resolved and spatially resolved nutrient data. And so a paper from Brian Pellerin, actually back in, I think, 2012 or 14, really showed kind of improvements to the dead zone kind of hypoxia models if you used continuous nutrient data from kind of Morgan City, Atchafalaya outflow versus the kind of seasonal averages that we typically rely on. We also know that there are a number of commercially available in situ sensors that can help kind of get that better, kind of more time-dense data. These typically take two forms, and nitrate is sensors that measure nitrate concentrations in the water are the main kind of market right now for nutrient sensors. They tend to either be wet chemistry based or optical based, and there have been, you know, optical and wet chemistry nitrate sensors for decades now. Phosphate, ammonium are other analytes that you can measure for, but those are typically only as kind of wet chemical analyzers and have been a much smaller kind of portion of the market. And when we look at, you know, this is one of the methods that NASA and some other groups use to think about technology or integration readiness levels. A lot of the nutrient sensors that are currently out there they're commercial, right? You can go and you can buy one. You can plan to kind of use that. But a lot of them have also been at prices or at levels of usability that have historically excluded some potential users. So, for example, state monitoring agencies or groups that maybe don't have a postdoc level scientist to run an optical nitrate sensor. Folks who, maybe have some funds, but not, you know, the many tens of thousands that it costs these days to purchase some of these. And so this has really led to really almost 10 years now of work to try and increase the diversity of sensors on that market, so that if you are monitoring, you know, coastal waters or fresh water for that matter, you know, you might be able to find a nutrient sensor that fits your purpose and also would fit your kind of budget and capabilities. This work really started in earnest around 2014 with the Interagency Nutrient Sensor Challenge. This was developed from a coalition of federal agencies. It was supported by the Alliance for Coastal Technologies, who is the testing partner. And it involves soliciting kind of newer to the market sensors that would be tested against kind of their stated specifications in the lab, as well as, you know, those more dynamic, challenging conditions in the field, from freshwater in Michigan to really pristine, low nutrient waters in Hawaii, and then of course this picture is from the Choptank River, kind of higher nutrient conditions, but also high fouling in Maryland. This challenge ultimately evaluated 6 nutrient sensors. 3 were nitrate plus or minus nitrate. 3 were phosphate. It represented 4 different companies that were working in this space. The evaluations from all of that work are available still on the ACT website, and provide really detailed and consistent across the different sensors results from these lab and field-based challenges. This work was followed up again by that Challenging Nutrients Coalition with a number of other efforts. So visualizing nutrients, action challenge. There's more recently been a nitrogen sensor challenge to work in septic systems, which is really interesting. But one thing that none of these efforts have been able to do very well is actually test how ready the sensors are, but also we are, to integrate some of these newer sensors into existing monitoring programs and systems. So, for the most part, if we already have some monitoring going on, right, we don't necessarily want to have to duplicate all of that in order to add a nutrient sensor. But that has really been a question, and one that we haven't been able to start to test until now. And so starting in about 2018 to 2019, with funding basically still from EPA and no IUs through ACT, through GCOOS. So we've been kind of just all working together on this for many years. We really wanted to try and get at this operational readiness, this idea of integration into existing systems or existing programs. And so this kicked off in 2018, 2019. We purchased 5 wet chemistry nitrate plus nitrite probes from an Italian company that had basically performed the best in that nutrient sensor challenge. We had 5 original partners spread across Florida, Alabama, Louisiana, and Texas. This was a picture from a September 2019 training workshop that we held here at UL, where everyone got trained on the sensors together, and then we kind of sent them out into the world. And then, of course, September 2019, so COVID-19 happened. At least 2 or 3 of our partners had to deal with pretty significant hurricanes. And so, we've learned some lessons. We've gotten some good data, which I'll share in a minute. But we kind of now have 3 core partners who are still actively working towards deploying or redeploying these sensors. And those are Sanibel Captiva Conservation Foundation in Florida, Louisiana University's Marine Consortium, or LUMCON, here in Louisiana, and then Mote Marine Lab, who kind of joined in, I think I said 2022, it might have been 2021, and they are in the process of trying to get their sensor out in the water kind of as we speak. I wanted to share a little bit of lessons learned from this process so far. So we've been at this since more or less kind of 2020. You'll see from some of the data that there are gaps because of these different, interruptions, I guess, shall we say. But through the work that SCCF and LUMCON have done, deploying these probes in kind of 2 different configurations, we have some lessons learned, some takeaways, and some things that are informing how we move forward. So we've really kind of started doing this testing of the integration into 2 ongoing systems and stations. So SCCF down here, LUMCON over here. This is the probe that we've been working with. It's a wet chemistry analyzer, so it uses a microflow loop reactor. It uses that vanadium chloride reduction method to ultimately kind of like in the can measure nitrite plus nitrate, which we'll refer to as NOx throughout the rest of the talk. And so it pumps water in. This top piece is a reagent canister where all those reagents for the reactions are held, and ultimately, right, measures the colorimetric response. There are waste bags that then it puts the waste components into. And one of the things that we somewhat intentionally, maybe somewhat opportunistically did is at LUMCON, they worked to really integrate this sensor into their existing environmental monitoring program. At SCCF, they deployed a more kind of self-contained, so kind of its own data logger, its own kind of power sort of model. And so we can look at kind of performance and just how this worked at the two different locations and learn a few things that again, are informing how we move forward. So first, if any of you are familiar with LumCon, I'm sure many of you are. I'm sure many of you have been here for one reason or another. We're here in Terrebonne Bay in Cocodrie, and they have an ongoing monitoring program. You can kind of see on this, at the end of this dock, there are deployment tubes. They have a weather station. They have power, data, telemetry that goes to GCOOS that you can also find on the LumCon website. And so this is the kind of system into which we have been working to integrate the Systea-WIS nitrate probe. And one of the interesting things about this location is that, again, if you've been to LumCon, especially in the last 10 years, right, flood events are pretty common these days. And so we've been somewhat limited by cable length. And so the way LumCon has their system set up is the sensors are here, and then you run a cable to basically these upper areas where the power and data logging is run. That was not really possible for us, given again, cable limitations. And so part of, I think, something that we've learned is, the physical infrastructure and how robust it can be in the field, right, can often be somewhat limited by the sensors and by the components themselves. This is, again, the integrated system. So tying into a Campbell Scientific data logger, a commercial data logger that's really common. This is a little schematic of how this system is being deployed. We did, for these kind of pilot deployments, have sensors we're measuring every 2 hours. You can measure more frequently, but if you want to get, a month or more of a deployment and not have to replenish the reagents, then a 2-hour sensor sampling frequency is about right. They did also take reference samples, and actually at 2 depths, at the surface and then at the intake depth, which is down here a bit deeper down. The other location, which is part of SCCF's Recon Sensor Array at this Shell Point location, this was actually deployed as a more self-contained unit. And so it's deployed from this piling. And in this case, we're using a manufacturer-provided data logger. So this is an accessory that you can purchase. Again, about a 2-hour sensor sampling frequency. In this case, we had kind of less frequent reference samples. They were taken near the intake depth. One of the other differences between these two configurations is you can also opt for a finer intake filter. So this sensor had a very fine intake filter, which kind of better matched the filters used for the reference samples. And we'll talk about that in a minute. When we look at data from the integrated system, one of the things that you can see is, we kicked off this project right before COVID. So obviously a lot of us had limited access to our labs, to the field. And so we definitely had some data that were not collected. And then we have hurricanes, in all of our systems. That is a challenge. And so, having to kind of go in and retrieve sensors so that they don't flood, or the data loggers don't flood, or you don't lose them, becomes, an important consideration. Generally speaking, we had a kind of lower range of nitrate in this system, so less than about 5 or 9 micromolar nitrogen for depending on the reference or sensor. Means were pretty similar, right around 1.5 micromolar. If we look at the self-contained system briefly, and again, it's the same sensor, but just deployed in 2 very different environments and also 2 different configurations. We had kind of a wider range of nitrate concentrations, but we also had periods, for example, winter 2021, dry season. You're always going to have lower limits of detection, right, that we can't really pick up with really most of our methods. And so In this case, we again had some of those COVID-19 protocols and kind of data gaps, some other, troubleshooting, maintenance. As I think many of you know, SCCF has been recovering from Hurricane Ian, so we don't have 2022 on here, but obviously these are some of the things that go into understanding how these, not just nitrate sensors, but any sort of sensors we put out in the system make it through. When we do just a really quick comparison between the reference and sensor measured nitrate values, it varies, right? And I will say that these are limited data. We are working to get a lot of these back out in the field and really build out these data sets more. But a couple of the things that that pop out are for the integrated system, where we had that, well, first of all, there are a few things that the integrated system can't do very well in terms of wash cycles and cleaning out between measurements, just because of limitations in the program for the Campbell Scientific Data Logger. There's also a bigger mismatch between the syringe filtration that we did for the reference samples and that intake screen, which in that kind of base model is 25 microns. So you can see where it looks like the sensor is consistently overestimating based compared to the reference samples. But this is also measuring, much more kind of small particulates and the nitrogen in there. So we have to be mindful of, some of these mismatches between how we do kind of lab dissolved nitrogen analyses versus a sensor that's really only screening out anything bigger than 25 microns. We saw a somewhat better agreement with the self-contained system that can do more kind of wash cycles between samples. But that also had a much tighter agreement between the reference sample and the intake kind of pre-screen. And so, one of the things that we definitely need to do more of going forward is make sure that we are, comparing apples to apples. I also want to point out that we have very different ranges in these systems. So we're really at this very low range in the integrated system in Terrebonne Bay, so less than about 2 micromolar. Whereas we have more of that kind of full dynamic range in the Caloosahatchee River and that estuary. We do have a data portal, kind of a pilot data portal with GCOOS. The SCCF self-contained system was reporting data to GCOOS that was being plotted. So this obviously just goes through 2021. But one of the things that we're doing going forward is the 3 WIS sensors that we're trying to get out, again, are now going to be more of this kind of self-contained model. We have some of those manufacturer data loggers and really try and get more of the data into the GCOOS data portal. Just a few last things, and then I'll put out the call for more partners. Biofouling, always going to be an issue in these estuarine systems. There are some fun ways that our collaborators have come up with protecting these sensors that have a lot of tubes and moving parts, and so happy to put you in touch with folks who have good ideas for that. And then finally, some of the lessons learned that we've gotten so far. So, the sensor works. Like if you put it in the lab, if you put it in the field, you can get nitrate plus nitrite concentrations out of it that do, especially if you have a wider dynamic range, kind of map onto what you see from reference samples. But there are pretty significant considerations in deploying these that come down to space, depth. These are not good sensors. None of the wet chemistry sensors are very good if you have locations where you might have very low tides and they might be exposed. You do need personnel, lab space, fume hood, some of the reagents need, lab prep. And ultimately, the kind of self-contained deployment approach seems to be the most functional right now. And in order to get that more fully integrated system approach to work, it really is going to take kind of the manufacturer working with data logger companies to make sure that program has more functionality. So I'll just end with that we are growing the network. So we've got SCCF and LUMCON basically getting ready to redeploy their sensors. In, I think, 2021 or 2022, we started working with Emily Hall and Jess Frankel at Moat Marine Lab. and they are also getting ready to put one of the kind of self-contained WIS probes out. Most recently, we've been working with Florida Department of Environmental Protection, and specifically this Big Bend Seagrasses Aquatic Preserve program. Kate and Trisha there have been really great. They're in the process of trying to purchase and install a commercially available kind of turnkey monitoring system. And we're basically working with them and a couple of different companies to say, okay, could we maybe try and get one of the kind of newer to the market optical nitrate sensors integrated in that. So lots of fun things happening now. And I just want to put out a call that we want to continue to grow this. So, maybe some of the folks on this call have monitoring going on and would like to try integrating a nutrient sensor. The funding that we currently have from EPA and NOAA via GCOOS is to purchase additional sensors, work with teams to kind of integrate those into existing networks, and then also to build more of this kind of community of practice, share lessons learned, and ultimately provide data. So if you're interested in getting involved, please shoot me an email. My email is there at the end, but you can also just Google me and reach out. I'd love to chat. Thanks to all of our partners, kind of old and new. It's been a lot of folks who kind of took this from a little idea to really a funded project that we've been able to turn into a more distributed approach, and we're excited to continue to do that. So I will stop there, and I think you can maybe kick me off, and if there are questions, let me know.
Thanks so much, Beth. That was great. I can't tell you how many times there's an event out there that I get calls and requests from folks. Do we have nutrient data co-located with any of these buoys or infrastructure? And sadly, for most of the areas, the answer is no. We go to satellite data, but it's not quite the same sometimes at depth, especially. So this is fantastic, really exciting to see the advancements here. We have a few minutes for questions if you want. We're a small enough group. You could just turn your cameras on if you'd like. You can raise your hand. We're all mesmerized.
I have a question. How much do they cost?
Yeah, so that's always the $1 million question, and they're not $1 million. Hi, Lisa. Thanks for the question. So part of the goal of this project and kind of all of the ones that have come before is to really try and look at this landscape of more affordable but still accurate sensors. I would say that the sensors that we're currently working with to get kind of ready to get out in the field, you're probably looking at 12 to 15,000, and that would be kind of sensor plus data logger for the WIS, but also with inflation and exchange rates. That's an Italian company. I can't quote it exactly. But the idea is, some of the stalwart kind of nutrient sensors that really came out of the oceanography community start at, closer to 30 to 40. So, that might not be possible, but some of these others can be. But I know you guys are doing some great stuff down in Texas. So if you ever want to chat about adding some nutrients to what y'all are doing, I'd love to.
Thanks, Beth. We also have a question.
Okay.
Lisa, did you have a response to that?
I just said, okay.
Okay, just making sure. And we'll be hearing from Lisa next week so we can find the areas of synergy at that time. And we also have a question from Philemon. Did the series of hurricanes affect any of the stations? And if so, how is the recovery effort going?
Yeah, the answer is yes. I think even before, right after we did that initial training, Dauphin Island Sea Lab, who was one of the original partners, got hit, right? And so, and it was really hard, at that point, right, you're rebuilding stations, physical, infrastructure, and some of these research questions come a little bit later. So it can be a pretty significant impact. In the case of, for example, LumCon, they had a model where they would go out and kind of bring their gear back in so that at least, it wasn't lost. So for example, they didn't get lost in Ida, but certainly that dock was damaged. It can take, months for people to be able to kind of go back. So yeah, these storm events do have really significant impacts. It's something that I think all of us who do monitoring are aware of, and you go into every hurricane season a little scared, but you try and minimize loss of data, but also instrumentation, but of certainly keeping your people safe. Yeah.
Thanks. I think we've got time for one last question. This one's from Greg. He said, "Great talk." I agree. And he said that you mentioned the inline sampling filtration. Are there any dogging issues associated with that?
Yeah, so there's basically a pre-screen. The base model of the Wiz comes with a 25 micron kind of base, inline at the filter intake. Sorry, the sample intake filter. And as far as I know, there haven't been massive issues with clogging there. These are reagent based, so you're going out at least probably once a month to replace reagents and do a little bit of maintenance. So kind of just brushing that off has kept those pretty good. The much smaller micron filter, which now I'm forgetting if it's 1 or 0.1, but if SCCF is on, they can remind me. That one is pumped, and so that one actually pumps water through that pre-filter, which is, I think, partly why we got much better agreement between that sensor and reference data. But those could clog. They do, again, require kind of that monthly scrub, and I think sometimes they would do it more frequently when, we're in those high biofouling periods.
Thanks so much, Beth, and to everyone for the questions. Next up, Jen, if you want to pull up Dr. Leben's presentation. Bob is a research professor, Emeritus, in the Department of Aerospace Engineering at the University of Colorado, Boulder. He's also a member of the Colorado Center for Astrodynamics Research. His work spans the areas of numerical modeling, computational fluid dynamics, geophysical fluid dynamics, satellite oceanography, and supercomputing. I should have really just said that he's Superman, all of the things that he tackles on a daily basis. His primary area of expertise is in satellite altimetry and its applications to ocean circulation and climate monitoring. And for more than 25 years, he's maintained a near real-time altimeter data system for monitoring mesoscale ocean circulation. And he's made significant contributions to more than 10 Gulf research programs. His work on the development and skill assessment of ocean nowcast and forecast systems has greatly enhanced safety for the offshore oil and gas industry. Today, he'll talk about his work related to monitoring, maintaining, and transitioning near real-time and historical altimetry products for the Gulf of Mexico into GCOOS, and also provide a review of recent significant oceanographic events in the Gulf. So thanks for being here, Bob. All yours. Bob, are you on mute? Can you please check and make sure your microphone's on? And maybe go back to slide 1 if you said anything that you would like us to hear. Thanks.
How's that?
That's great, but if you had your introductory slide, if you said anything on that, we were not able to hear it as well, so that's perfect. Okay. There you go.
Yes, I'm Bob Leben. I'm a research professor at CCAR. It's a center within the Department of Aerospace Engineering Sciences, the University of Colorado in Boulder. I've been involved in satellite altimetry since practically its inception, way back in the 80s, starting with GeoSat and going forward. In 1996, we actually developed a near real-time product for the Gulf of Mexico. Because of that effort, when GCOOS was looking for sea surface height for their data portal, they funded us to provide data from our near real-time system to GCOOS, so people could access NetCDF files and download animations of the data. They also pointed to a website that we ran for many years for the operational data in the Gulf of Mexico. Recently, we've had to move satellite altimetry, and I'll be going over that, but we do still have the capability to do daily sea surface height maps by using operational data now from the Europeans. Cross-cutting themes that we're interested in are, of course, data management and communications, making sure that people have access to satellite altimetry in the Gulf. I've also been involved in some sea level work, monitoring long-term environmental change due to sea level change. One of my favorite things has always been outreach and education. For that, there's nothing better than near real-time data. I've also been involved a little bit in numerical modeling and forecasting. A talk about near real-time data wouldn't be complete without a real-time map from today. This is Gulf of Mexico sea surface height from data collected up through about midnight last night. This comes through the Copernicus data system, which we're now using. The Europeans are now on the cutting edge of operational satellite altimetry, and we've moved to using their data product to make our near real-time maps. Fortunately, we also have a nice SST product from Nan Walker at LSU. This shows an overlay of the sea surface height map that we made from the European data stream, near real-time data stream, overlaid on Nan's image from today. Her GCOOS 16 image is excellent in the fact it's produced nightly, and because of compositing of so much imagery, she's able to get usually a cloud-free image. Though earlier this week it wasn't quite cloud-free, but luckily we got a very nice one for today. We've been doing this for a long time. I remember that one of the first times I gave a presentation to the GCOOS board was way back in March of 2015. This shows a map that I downloaded for that day from our website, which was allowed you to actually produce custom maps and download them. And also we had the ability to overlay the altimetry on SST, much as I'd done with Nan's product and the Copernicus data system data that we're now accessing in near real time. When we ran the outreach altimetry site for NASA, we actually had allowed users to make their own interactive graphics files, custom data, custom mapping of the data, and combining of the imagery. And we had quite a number of users accessing that. When we finally had to shut down the server in, which I'll talk about a little bit more, we were approaching over 200,000 images produced by users each year, and this just grew. Unfortunately, NASA got out of the outreach program in altimetry because altimetry became operational. It was handed over to NOAA, and because of that, our outreach funding that we were getting through NASA went away. Our initial work in outreach for near real-time altimetry actually started way back in 1996. We were the first site to produce daily maps in the Gulf of Mexico, and then globally using a combination of the available near real-time altimetry. And because we heard Frank Mueller-Carter talk a few weeks ago, I thought I'd show an overlay map that we'd made for one of our initial papers on real-time altimetry. We were combining TOPEX and ERS data at that time and producing daily maps. And that daily operational product started in 1996. We were able to run that for over 20 years continuously. Back in 2019, I gave an update on the status of the system, and we were running into issues. Our near real-time system database system had been hacked. we are running this kind of on a shoestring budget, and we're using obsolete servers. We changed the Mac OS system so much that we couldn't do updates, and we were finally having trouble with hackers coming in. So we had to take down the old system, and we were thinking, oh, what we can do is actually update the system and try to continue to do real-time data processing using RADS database, which is a radar altimeter data system out of Europe, out of Delft. We were able to move our servers and stuff over to a new data center, and this was all associated with a move when CCAR, which is a center in aerospace engineering, moved over into new University of Colorado Aerospace Engineering building. This was an update I gave to the GCOOS meeting in April 3rd, 2019. So I'd like to update where we're at now, 4 years later. You can see the aerospace building is there. We moved in that summer, and we were, because of the problems associated with moving to RADS, we decided, and well, there's a variety of issues, moving in the new building, COVID-19, graduation of students and programmers, and just the complexity of near real-time data streams made the porting to RAD just not something I wanted to try to do as in semi-retirement. However, during 2020 to 2021, I was able to use the data from the Copernicus data system and produce a comparable near real-time product to what we've been doing with near real-time data collected from a variety of sources through the old CCAR system. So that system is now operational. We have near real-time data for the Gulf of Mexico that is produced daily. Historical data products suitable for research are available through June 2022. This is based on the Copernicus system. Actually, when they do their updates of their historical data products, they call it a multi-year delayed time product, which is a research quality data product, not a near real-time product. This shows a timeline of modern radar altimeters, and I kind of wanted to show what got us in a pinch here is typically in the past, 2 satellite sampling was required to map mesoscale. And we started doing near real-time processing in 1996 and continue that through 2016. And you'll see at about the 2016 time period is when there was a flurry of launches. And this is when a lot of European satellites and NASA satellites, multi-satellite altimetry really took off for nadir type altimetry, measuring sea level right below the satellite. So it went from being a kind of a 2 satellite, 3 satellite process to now, in fact, 6 operational satellites are working as of today. And the nice thing about that is all that along track data and gridded data are available in real time, near real time from the Copernicus website. Because of that, I elected to go ahead and change our processing over from, this is an absolute dynamic topography that's provided by Copernicus. It's a little bit different than our Gulf of Mexico product because the background mean is different. It's based on estimates of the mean dynamic topography, not a model mean. We got a model mean from a data assimilation modeler onto our product, which I think works a little bit better. But the important thing to see here is just the amount of sampling and the accuracy that you now get from 6 satellite sampling. This is the absolute dynamic topography mapped by the Copernicus system and the sea level anomaly error associated with that optimally interpolated map. We process that to make a sea surface height map based on our own model mean. And I just wanted to show you that day to day, it's a long track sampling can vary quite a bit. This shows 1 day of sampling from April 6, 2018 for the long track sampling from each of the flying altimeters at that time, and then on April 7th. But you see that there's quite a bit of multi-satellite sampling available now. This was when we first started looking at the potential to try to use the new Copernicus system. So near real time is interesting in the Copernicus system. The way we worked with our original Gulf of Mexico system was we'd do it the best map we could make today, and in 30 days we'd make a final map that would have a centered time window that would give you a good historical map. Copernicus does a similar kind of thing. They have a they'll make a map today, which is what I downloaded, the day zero map, but they also update that map for a week until they come to what is they call their day 0 plus 6 days. That's the near real time map that is then available with the website going forward. But on today's date, you can get a map with data up to today. But if you wait a week, you'll actually can get a better map that's with data up to today plus the 6 following days coming after today. So this is their real-time data stream. It's quite nice. This also means that when we reprocess the data, download the data, we can update the data over time too, just as they do. They also then go back and do a multi-year analysis, and they use their center time window, reprocess all the data for scientific work, and then post that. The current multi-year time series runs all the way through June 23rd, 2022. You can get daily sea level maps from 1993 through June 23rd, 2022 for scientific work. So this just shows you the difference between the day 0 for, this was a week ago, I think last Sunday, and the day 0 March 13th map that you could make on March 13th, and then the day 0 plus 6 days of extra data on March 13th, sea surface map produced 1 week later. And if you go back and forth between these two, especially if you look at small scale eddies, you can see that there's been just a subtle improvement in the near real-time product between with the addition of the extra sampling. And this is overlaid on NAN's product, which is a nighttime composite. So it's a single image produced daily. But it shows you that the altimeter is with this long track sampling is not a conventional satellite product. You have to do some kind of interpolation from the long track data. In summary, we've produced a near real-time data set derived from Copernicus, combined with our existing CCAR mean, which is able to map the loop current and the eddies quite well in near real time. And this is what the product we're now providing to GCOOS. We also can provide the delayed time multi-year data set, which is processed in a similar way from the multi-year product that Copernicus releases, usually about a year or a year and a half behind real time. Updated data sets are available, publicly shared through the GCOOS website. We also have been working on SST, SSH analyses, which we're producing with NAN's product. Just a heads up that altimetry is changing. We're going from just a single nadir measurement to a swath measurement system. So it'll be much more similar to imagery in terms of the coverage. The VISO and Kinect teams, which provide all the processing capability to Copernicus, have just released some of the SWOT nadir data. SWOT was launched last December. This will be the first wide swath altimetry. It's sea surface height determined from interferometry, and adding this data stream to operational data streams will be an interesting effort. But VISO and Kinetis are taking the lead on that. And the initial nadir passes is now are available for downloading for a couple days. I'd like to acknowledge the support I've gotten from GCOOS. We also had a little bit of support from National Academy to work on an altimetry-based statistical forecast model for the loop current system that I did with George Forrestal. We use this support to really look over the Copernicus data sets and get to more of an operational near real-time system based on the data now coming through the Europeans. Also, I'd like to thank Nan Walker and Larry Kaig for the excellent imagery they have available for downloading from the LSU website. There's nothing better than being able to have a daily map of almost cloud-free imagery in the Gulf every day to overlay the satellite altimetry on. I think I will stop there. I was going to show a little bit, walk through the loop current eddies of 2023, but I think we're probably getting long on time. Thank you.
Thanks, Bob. First, I want to say thank you. Over all of the years, I know it doesn't sound, as impressive to folks who aren't aware, but 10 major Gulf research programs that you've been a part of, and this data you've evolved with over the years has been really instrumental in serving as a foundational layer for a lot of products, and not just on the altimetry side of things, but like even now it's laid the foundation for a lot of the marine biodiversity observation network seascapes, and the foundational work has just been really impressive and valuable. So thank you for that. I'm going to open it up for questions. We have a few minutes. Anybody would like to ask Bob anything?
Chris?
Yes, Philemon, go ahead.
This is for Bob. When will we be able to see the latest data in GCOOS? Because we had a very huge gap. We stopped in 2021, I believe.
Yeah, this data is available through today. The historical data goes through June of 2022 now. You guys have access to the FTP site. I just want to, we should get together and coordinate, make sure that you grab a whole new set of the archive. It might be that we just want to move to this new historical and near real-time stream and replace what existing CCAR data was there with this new data, because this will go on forward. We can update it. What we were doing was monthly. I think you were doing some monthly averages and things like that. So we should sit down and discuss exactly, what you would like, and we can produce it and host it from our FTP site to you. The data is on the FTP site. I noticed that you guys haven't grabbed it much lately, but
yeah, because we were not certain exactly if we are ready to grab the data, because there was a big thing that happened at that time when you got hacked. So I guess Atumo, if you are on, yeah, you're Atumo, you're attending this webinar. Please join us. Bob, well, I'll send an invite for the three of us to meet and try to catch up with the gaps.
Philemon, I've been downloading data from Bob Leben to our computer, and so I've processed all the for 2022 as well. I process those, and those are ready to be put up on GCOOS 5. So all the data is updated, and I have to just post them again on GCOOS 5, the newest version.
All right
But
then.
but
Look at
I've
that
been,
one.
yeah, I've been downloading data.
Yeah.
Okay, wonderful, Bob. Thanks a lot. Then the question is, it's more than academic. You don't have to meet.
Yeah,
Looks like Marian
you
is
might
on
want
top.
to go back and replace some of the historical data, so we have, all of the data is based on a standard processing back to, I think you have data
Oh,
from 2004 onward. But yeah, I've gone back. This data stream is on the FTP side.
okay.
I've had the process running in reanalysis done for quite a while, so I was hoping you guys were grabbing it.
Okay, I will work with Marion then to make sure that we have all the data for GCOOS posting since you did the reanalysis. So Marion, please note of that and keep me posted on development if you don't
Yep.
mind. Thank you.
Yeah, I will. I mean, as I said, I have been downloading the data, so I processed it to 2022 are ready to be put on GCOOS 5. We still have to get the other servers where we can see the data, and
Yeah,
the movie is ready as
that's why.
well.
Yeah, that's why Tumo needs to be involved because the other one is not updated. It
Yeah,
stopped
I
in
know.
2021, so we'll have to change that. All right, thank you.
We're coming up on the hour, so if we could follow the conversation offline on some of this, I think that would be okay. Does that work for you, Philemon, Marion, Bob?
Sure.
Oh yes, definitely.
Yes.
Okay, great. We're up on the hour. I want to say thanks to our speakers, Beth and Bob. Technical support from Jen. I know you're hiding back there still. Our communication support from Nadine Slimak, and to all of you for joining us today. We hope to see you next week. We'll hear from two folks who are working on the imaging flow cytobot, Dr. Ken Hoadley from the University of Alabama and Dr. Lisa Campbell from from Texas A&M University, College Station. And until then, be well, and we hope to see you soon. Thanks, everybody.